On June 18, 2023, 5 people descended into the North Atlantic Ocean inside a 22-foot experimental submersible named Titan. Their destination was the wreck of the RMS Titanic, resting nearly 3,800 meters below the surface. The dive was expected to take approximately 2 hours. Less than 1 hour and 45 minutes into that descent, communications stopped. There was no distress signal, no emergency transmission, no final words. For 4 days, the world watched a countdown based on oxygen supply. Search aircraft scanned vast ocean grids. Naval vessels deployed sonar. Underwater microphones detected ambiguous sounds that fueled hope and speculation. But long before the global search intensified, physics may have already determined the outcome. To understand what happened inside Titan, we must analyze its engineering design, the structural behavior of its materials, the environment it entered, the regulatory framework surrounding it, and the sequence of events that unfolded. This is not simply a story of loss, it is a case study in the limits of engineering at extreme depth. The extreme environment. Pressure without mercy. At sea level, atmospheric pressure measures approximately 14.7 pounds per square inch, psi. At 3,800 meters, the depth of the Titanic, external pressure exceeds 6,000 psi. That means every square inch of Titan's hull experienced more than 3 tons of compressive force. This pressure is constant and uniform. As the submersible descends, pressure increases steadily. There are no pauses, no fluctuations, no moments of relief. The deeper the vessel travels, the greater the compressive load. At these depths, even microscopic structural weaknesses can propagate under stress. Materials that perform reliably in air or shallow water behave differently under sustained high compression. The ocean does not allow gradual failure. When structural limits are crossed, collapse occurs instantly. The design philosophy, innovation over tradition. Titan's design departed from traditional deep submergence engineering. Most submersibles capable of reaching Titanic depth use thick, spherical titanium pressure hulls. The spherical shape distributes compressive forces evenly, minimizing stress concentration points. Titan used a cylindrical carbon fiber composite pressure hull capped with titanium end domes. Carbon fiber is known for its exceptional strength-to-weight ratio. It is widely used in aerospace and high-performance engineering. However, its mechanical behavior depends on the direction and type of force applied. Carbon fiber performs exceptionally under tensile stress, forces that pull outward. In deep-sea applications, the dominant force is compressive, water pushing inward. Composite materials like carbon fiber consist of layered fibers bonded with resin. Under repeated compressive cycles, microscopic damage such as delamination can occur. These separations between layers are not visible externally but can reduce overall structural integrity. Titan had reportedly completed multiple dives prior to the final mission. Each dive subjected the hull to extreme compression at depth and decompression during ascent. These pressure cycles are significant because cumulative fatigue can alter the structural properties of composite materials over time. Material science, fatigue and failure, mechanisms. Understanding what happened inside Titan requires examining how composite materials behave under repeated compressive stress. Unlike metals such as titanium, which typically exhibit predictable deformation before failure, composite materials can accumulate hidden internal damage. Tiny cracks in resin layers, fiber breakage, or bond separations may develop gradually. Under increasing external pressure, these microscopic flaws can expand. If a localized weakness reaches a critical threshold, stress redistributes to surrounding material. At 6,000 psi, that redistribution can trigger rapid structural collapse. Another important consideration is the interface between different materials. Titan's hull combined carbon fiber and titanium components. When materials with different elasticity properties are bonded together, stress concentration points can develop at the interface. Under uniform external compression, these transition zones may experience uneven load distribution. While investigations continue to analyze the precise initiation point, the most probable mechanism remains catastrophic structural failure of the carbon fiber pressure cylinder during descent. The mission profile: a routine dive. On board Titan were 5 individuals: the company's CEO, a British billionaire explorer, a Pakistani businessman, his 19-year-old son, and a French Titanic expert with extensive deep-sea experience. Each passenger reportedly paid approximately $250,000 for the expedition. The dive plan was straightforward: launch from a support vessel, descend for approximately 2 hours, reach the Titanic wreck site, conduct exploration, and ascend. Communication during descent relied on acoustic messaging systems. Radio waves cannot travel effectively through seawater, so short digital acoustic signals are used for contact between submersible and surface support. For over an hour, descent appeared routine. Then communication stopped. The moment contact was lost. Approximately 1 hour and 45 minutes into the dive, Titan ceased transmitting. It had not yet reached the seafloor. Pressure was still increasing. When a deep-sea vessel loses communication but remains intact, it may resurface or re-establish contact. However, if the pressure hull fails catastrophically, communication ends instantly. Implosion at Titanic depth occurs in less than a millisecond, faster than the human nervous system can register pain. A blink of the eye lasts roughly 300 milliseconds. Structural collapse under 6,000 psi occurs hundreds of times faster. In such an event, internal air compresses violently. Structural components accelerate inward. The vessel disintegrates almost instantaneously. The absence of a distress call strongly suggests catastrophic structural failure. The search and global response. Following the loss of communication, international search efforts began immediately. Aircraft deployed sonar buoys. Naval vessels scanned vast ocean areas. Remotely operated vehicles were mobilized. Titan reportedly carried approximately 96 hours of breathable air. That figure became the center of a global countdown. Hydrophones detected intermittent underwater sounds, which fueled speculation, but experienced marine engineers understood that if the pressure boundary had failed, survival would not be possible. 4 days later, debris was discovered near the Titanic wreck site. The titanium end caps were located separately from the main hull. The carbon fiber cylinder had disintegrated. The debris pattern was consistent with implosion during descent. Internal conditions at the moment of failure. Inside Titan, during descent, conditions would likely have appeared normal. The occupants were seated closely together in a compact cabin. Lighting was controlled. Systems were minimal but functional. If microscopic cracking occurred within the hull as pressure increased, it may have produced subtle sounds indistinguishable from normal structural noise. Deep-sea vessels often produce creaking sounds under pressure transitions. However, once structural integrity was compromised beyond a critical threshold, collapse would have been instantaneous. There would have been no prolonged awareness, no extended reaction time. The event would have concluded before conscious perception could process it. Regulatory framework and industry implications. Titan operated without full classification approval from major marine certification bodies. Traditional deep submergence vehicles undergo extensive third-party testing and verification to ensure structural reliability under extreme pressure. Certification processes are rigorous because deep-sea engineering leaves no room for error. Conservative safety margins are built into certified vessels to account for material fatigue and unknown variables. The company behind Titan emphasized innovation and flexibility, arguing that traditional certifications slowed progress. Critics contended that certification standards exist precisely because extreme environments demand conservative engineering. In the aftermath of the incident, regulatory agencies initiated reviews of private deep-sea tourism operations. The event has reinforced the importance of third-party verification when human life depends on structural integrity at extreme depth. Lessons from deep-sea engineering history. Deep-sea exploration has always involved risk. Early bathyspheres and experimental submersibles faced structural challenges that shaped modern standards. Over decades, engineers refined spherical pressure hull designs and conservative safety factors. The deeper humans travel, the narrower the margin for structural error becomes. Titan represented an attempt to rethink deep-sea accessibility, but the environment at 3,800 meters does not reward reduced safety margins. It tests every assumption. Prior warnings and industry concerns. Long before the final dive in June 2023, questions had already been raised within segments of the deep submergence engineering community regarding Titan's design and operational approach. These concerns were not rooted in hostility toward innovation. They were rooted in physics and experience. Deep-sea submersible engineering is a niche field shaped by decades of trial, failure, redesign, and strict certification standards. The reason most extreme depth vehicles rely on thick, spherical titanium hulls is not aesthetic preference, it is mathematical inevitability. At several thousand meters below the surface, compressive forces demand geometry and materials that distribute load predictably and conservatively. Titan diverged from that model. Several marine engineering professionals reportedly questioned the long-term behavior of a carbon fiber composite pressure hull under repeated full-depth cycles. Composite materials, while strong and lightweight, behave differently from monolithic metals under cyclic compression. Unlike titanium spheres that can be non-destructively tested for microscopic deformation and fatigue, layered composites introduce complexity in inspection. Internal delamination can occur between fiber layers and resin bonds in ways that are difficult to detect without specialized methods. In addition to material concerns, there were broader questions about classification. Major marine certification bodies provide third-party verification of design calculations, material selection, pressure testing, and fatigue limits. Titan operated without full third-party classification approval. The company maintained that internal testing and engineering assessments were sufficient. Critics argued that third-party certification exists precisely to remove subjective judgment from safety-critical design decisions. The debate centered on one essential question: how much margin is enough at 3,800 meters? The pressure cycling effect. One of the most critical engineering discussions following Titan's loss revolves around pressure cycling. Every descent to Titanic depth exposes a pressure hull to more than 6,000 psi of external force. Every ascent relieves that pressure. This repeated loading and unloading cycle is known as pressure cycling. In metallic structures, engineers have decades of fatigue data that quantify how many cycles a material can endure before microscopic cracks propagate into structural failure. Composite materials behave differently. Carbon fiber reinforced polymers consist of directional fibers embedded in resin. Under compressive stress, fibers can buckle microscopically within the matrix. Resin can develop micro cracks. Bonding interfaces between layers can weaken. Each cycle adds incremental damage that may not be externally visible. If Titan's hull had undergone multiple full-depth dives, the cumulative effect of those cycles becomes a central technical consideration. Even if each individual dive remained within calculated limits, repeated exposure can gradually reduce structural resilience. In extreme pressure engineering, margins are not simply about surviving one dive. They are about surviving the 10th, the 20th, or the 50th. Acoustic health monitoring, theory versus reality. Titan reportedly incorporated an acoustic health monitoring system designed to detect abnormal stress signatures within the carbon fiber hull. The concept behind such systems is based on the idea that microscopic fractures emit detectable acoustic emissions before catastrophic failure. In controlled environments, acoustic emission testing can identify stress concentrations and material anomalies. However, the challenge lies in interpreting signals under real-world conditions. Deep-sea environments introduce background noise, temperature variations, and complex stress patterns. More importantly, even if microfractures are detected, the time between detectable anomaly and structural collapse at 6,000 psi may be extremely short. The rate at which compressive failure propagates in composite materials under extreme external pressure can outpace response protocols. Emergency ascent requires releasing ballast and achieving positive buoyancy. That process takes time. Structural collapse at Titanic depth does not. Even with advanced monitoring systems, there is no guarantee of a survivable warning window once critical stress thresholds are exceeded. The titanium composite interface. Another technical area of interest is the interface between Titan's carbon fiber cylinder and its titanium end caps. Whenever two materials with different elastic moduli are bonded together, stress concentrations can arise at the boundary. Titanium and carbon fiber respond differently to compressive loads and temperature changes. Under uniform external pressure, even slight differences in deformation characteristics can introduce localized strain at the joint. At moderate pressures, such strain may remain within tolerable limits. At 6,000 psi, small mismatches become amplified. Engineering such interfaces requires meticulous modeling and validation testing. Even then, real-world variables can differ from simulation assumptions. If stress concentration developed at the bonding interface, it could have initiated localized structural compromise that propagated into full hull collapse. Investigators continue to analyze recovered debris to better understand how loads were transferred across these material boundaries. Viewport depth rating and structural redundancy. Deep-sea acrylic viewports must be specifically rated for target depths. Viewport thickness, curvature, and material properties determine how compressive force is distributed across the viewing window. While debris evidence suggests the primary carbon fiber cylinder failed, scrutiny has extended to all pressure boundary components, including the viewport. In extreme medium pressure design, redundancy is often built into critical systems. Traditional submersibles rely on conservative multipliers to ensure structural integrity beyond expected load limits. When design philosophies prioritize reduced weight and cost efficiency, redundancy margins may be narrower. At 3,800 meters, narrower margins translate directly into reduced tolerance for unforeseen stress factors. The timeline reconstructed. Reconstructing Titan's final descent provides additional insight. The submersible began descending normally. Descent rate and acoustic communication were functioning. As the vehicle approached greater depth, external pressure increased steadily. Approximately 1 hour and 45 minutes into the dive, communication ceased abruptly. If a gradual system malfunction had occurred, acoustic signals might have degraded or intermittently resumed. Instead, communication ended entirely. This timing strongly aligns with a structural event rather than an electronic failure. An electronic malfunction would not prevent buoyancy-based emergency ascent unless structural integrity had already been compromised.